So there are three terms here: element, baud, and bits. And you have to understand the difference between the three. So this bit consists of two elements, a long pulse and a short pulse. That is one bit. If you want to send a 1, you send a long pulse followed by a short pulse. Okay? If you want to send a 0, the coding will tell you what is the code for 0. It could be that it is a short pulse, 2 short pulses maybe. So the coding will tell you what a 0 looks like, what a 1 looks like. 0 and 1 do not have to be just 5 volt and 0 volt. So these are elements, and this is a bit. And here the coding is very simple. It says that you could have minus 5 volt or plus 5 volt. So and in some cases the coding says that it is not the level, it's the transition which makes 0 or 1. So if we transition from low to high, that is a 1. If we transition from high to low, that is a 0. Actually, sorry, this is shown slightly wrong. If we transition, so this is the bit, this is a bit. In this bit duration, there is a transition, that is a 1. If there is no transition, so this actually does not really show a 0. If it was continuing here, then there is no transition during that bit time. That would be a 0. Alright, transition is a 1, no transition is 0. And there are many different kinds of coding, and there is advantage and disadvantage of each kind of coding. Okay, and we will learn some of them. But anyway, so the idea is, in each of these cases there is a smallest element that can be, so in this case, for example, the smallest element can be equal to 1 bit time, right? And that is called a baud, right? In this case, there are two elements, one is big, one is small. The smallest one is the one that tells you how much is the baud rate, because the smallest element determines the quality of electronics that you need to use that coding, right? If it is very small, nanosecond, then you need much better electronics than if it is millisecond. So the baud rate determines the quality of the electronics, and the bit rate is what you are interested in, right? The electronics and doesn't really know the bits, but what they know is, and so how many bits are coming out is what you are interested, as a user you are interested in, but the electronics quality and price depends upon the baud rate. And some combination of elements actually is called a symbol. So I didn't want to use the word symbol here, but we could, for the time being, we would call this one thing as a symbol, because generally when we go into the later part of coding, you will notice that we don't send a bit actually, we send multiple bits at a time, a bunch of bits at a time, and that is what we generally call a symbol. So we'll come to that in a minute. So we'll reserve the definition of symbol, and so we'll have element, baud, and bits, right? Okay. Now, if we just keep sine waves for, so I just showed you some square waves, but let's forget that for a minute and just think about sine waves. If you have a sine wave, then you can modulate it in different ways. So for example, if the amplitude is small, that is a 0. If it is large, it is a 1. 1 is 0. So that would be called amplitude modulation. When you want to send a 0, you just send a small pulse, small waves. When you want to send a 1, you send big, high waves. Or you could change the frequency. So when you want to send a 0, you have a low frequency. When you want to send a 1, it is a big, high frequency. That is frequency modulation. Or you could change the phase. When you want to send a 0, the phase is 0. When you want to send a 1, the phase is 180 degrees as shown here.
Yeah.
Yeah, okay. So basically you have to determine what is the phase of this pulse, of this wave. If phase is 0 as shown here, then it is a 0 bit. If the phase is 180, then it is a 1. You see, this is a phase. At the beginning of the bit, we generally indicate the wave will go up, right? But it is going down. So phase is 180. Yeah.
Do you know which is the fastest of these to do to modulate between the 0 and the 1?
Which one of the amplitude, frequency, and phase?
Uh-huh.
All right. So the question is, which one is the best? Amplitude, frequency, and phase. I would simply say which one is the easiest right now, because best would come out later, right? So the easiest thing is amplitude, right? If I say loudly, then you can easily calculate, you can see that the amplitude is high, right? And if I say slowly, then it's a 0. And so that's the easiest thing to figure out. Amplitude can be easily figured out. And then frequency is kind of difficult. If I say in a very tiny sound voice, then it is a 1 and a 0. So in general, for example, female voice is much higher frequency. And so that is difficult. We can still, human beings can figure out in female and male voice. But at the electronics level, it kinds of, becomes more difficult. And the phase is even more. And now the question is, which one is best? Basically, I haven't defined the best yet, so I'm not going to say, but basically it is very easy to interfere with the amplitude modulation. Alright? Frequency modulation, it is very difficult to interfere with, because if you introduce exactly the same frequency, then it is different, but if you introduce any other frequency, I can easily filter it out with a frequency filter. Right? So you will not affect my zeros and ones. So frequency, you can see right there that the frequency modulation is better. The more difficult things are generally better, right? So what it is the life started with amplitude modulation. We call it keying here. In a minute I will explain why keying and what is the difference between keying and modulation. So life started with amplitude, and then people felt, no, we can also do with frequency. It is better in some sense, but more difficult. And then they said, why can't we do with phase as well, right? Now why we call it keying as opposed to modulation? Modulation is generally for the analog, continuous variation. So suppose you want to send a sound like we used to do before, telephone. We used to modulate the sound on an electronic sine wave and send it through a wire. That would be modulation. But now we don't send the sound that way. Now what we do is we take your sound and make it zeros and ones. So we make 8 bits out of each level, and then we send zeros and ones. So we call it keying. Keying is basically 0 and 1, binary. Okay? So when I say ASK, it is binary. When I say amplitude shift modulation or something, then that will be continuous wave that can be put on a sine wave. Is that clear? That it doesn't have to be 0 or 1. The amplitude could change continuously. Yeah.
Is the difference there in how it's interpreted or the signal itself?
So the signal itself is in the case of modulation is continuous signal, and so input signal is continuous. The transmitted signal is continuous in all cases anyway, but the input signal has a continuous amplitude, and then it is modulated on some kind of transmitted signal, and then when it is received, we get back the original signal. Right, so that is modulation part, right? In the keying part, you send zeros and ones, and you get all this thing which is actually continuous, if you want to call it continuous, and then you get back the zeros and ones. All right. So now we can continue this, and so people felt that instead of zeros and ones, why don't we do differential, where you don't worry about the original signal, you just worry about the previous symbol. So this is a 0, and since there is a phase shift, this is a 1, and then there is a phase shift, and therefore this is a 1. Then there is no phase shift, and therefore this is a 0. So in this case, basically you don't have to worry about what the originally this, where the phase was, but basically the previous bit, if there is a phase shift in this bit, it's a 1, and if there is no change in the phase shift, then it is a 0. Yeah, question?
So could there be a problem if like one of those phases is lost and everything going?
No, actually you can't lose a phase. Basically what it is in this case, much more is the clear advantage of differential is you can put a positive wire on the negative side and negative wire on the positive polarity, it's independent. Because you really are not looking for plus or minus, you are looking for a change. Okay, yeah, go ahead.
So all the time the first bit should be known at the receiver, yes?
Okay, so the question is, for all these cases, the first bit should be clearly known whether it is 0 or 1, because you could know. So in the differential case, actually, you probably don't need that. Because when there is a change, now this is a 1. Whatever the previous one was, of course, it was something different, right? So you know this one. But in other cases, in the previous cases, that was not differential, then there is a problem of synchronization that you really need to know where the bits start. For example, if you start the bit right in the middle here, there will be a problem, right? So so you want to synchronize the bits correctly, and then polarity is also important, because if you are thinking about positive and negative, and so what we do is in the beginning we do synchronize. So whenever you set up a connection, there is a synchronization pattern sent, and if you receive that pattern, then you know, okay, we are right on time now. We are receiving the bits correctly. Now we can do the communication. So that part we are missing right now, but basically let's assume that somehow we know where the bits begin, and we look for the transition at that point. Otherwise, if you look at the wrong point, you will get only a zeros. Right? I mean, there won't be any transition. So you have to be exactly aligned, and then also in some cases you need to know the correct phase and correct thing, and this and all that is done in the beginning. So now this is a differential. Now this is the name, and the name is important. Differential BPSK, binary phase shift key. Okay, so binary means 0 and 1 only. And phase shift means we are only going to find out between 0 and 1 by phase shift, right? And differential means only from the last bit, as opposed to from the absolute position, right? And you don't have to have binary, you could have quadrature. So what you could do is you could take 2 bits at a time, and 1 would be 45 degrees, 1 0 would be 135 degrees, 0 0 would be 225 degrees, and 0 1 could be 315 degrees. And so whenever you see this shift, in this case it is 45 degrees, in this case it is 135 degrees, in this case it is 225 degrees, and so on and so forth, you know what bits are coming. So now you can get 2 bits in the same time. So this will be twice as fast compared to BPSK. QPSK will be twice as many bits per second. The only complication here is, here we only need to know whether the phase is 0 or minus 180. Here we need to know whether the phase is 45, 135, 235. So you have to be able to distinguish between the phases much more carefully. Yeah.
So the error performance for the QPSK is worse than differential BPSK.
This will have very little error. This will have more errors. That's a good point. And one way to represent this, we won't be plotting waves anymore. We will be representing them on a chart like this, where 0 has a phase of 0 and 1 has a phase of 180 degrees. And in QPSK, 0, 1, 1, 1, 1, 0 and 0, 0 are shown right here. And you could put this 0, 0 wherever you want to, and then you tell the receiver that this is my coding, and they will get the same coding, but they have to distinguish between the 4 angles. Yeah.
Why would the QPSK does not have any 0 representation?
0 here? Yeah, right. See, because basically you need 4 combinations. Now you could make 4 combinations here, like, you could do 2 here, 0, 180, 0, 90, 180 and 270. Right? And now I think that should be equally good, but I really don't know. I mean, like this, in this example, it is not the case, right? And most of the examples that we'll see, if you have 4 phases, they will distribute it like this. And maybe, there's some reason which I don't know at this point, okay? But right now, when I say BPSK, you know that this is basically that, 0 and 180. They could have shown 45 and, 225 or something, and that would be equally valid, yeah.
May I tell the reason that why they're choosing this way? They choose in a way that the neighbors have only difference in 1 bit. So if the error happens, it's more probable that 111 be detected as 10 or 01. So we will have error only in 1 bit. So because of that, the code words that are different in 2 bits, they will put them in as far as possible. So if they, it will be less probable that they will detect it instead of each other. So the error will be decreased.
Okay. So let me say, I think you answered a different question, but that's an important consideration. So C asked the question, but why it is at 45 degrees and not at 0 degrees? And you answered another question, and that question is that these numbers are not arbitrarily put here. 00 to 01 there is only 1 bit change. 01 to 11 there is only 1 bit change. And 11 to 10 there is 1 bit change, 1 bit change. Because it is quite possible that you might mistake this phase for one of these two. In either case there is only 1 bit error. Right? That's the question you answered, right? Yeah, so that basically means that you cannot put 00 here and 11 there. That would be wrong, because then you will get 2 bit errors, for a little mistake. But that question of 45 versus 0 degrees still remains. All right. Now, why stop at 4? Okay, so this is called quadrature amplitude modulation, QAM.
Same as QPSK.
Eh?
Same as QPSK.
Yeah, same as QPSK, QAM. Quadrature amplitude and phase modulation. Now I will tell you why amplitude is coming in. But right now, in this case, there is no amplitude. All those 4 points have the same amplitude. What is the amplitude? Amplitude is the distance from the origin. So this point has an amplitude of that one. This point has the same amplitude. This point has the same amplitude. This point has the same amplitude. So all 4 points are different phases only. Right? But there are 4 points. So we call it 4 QAM. But you don't need to have 4. You could have 16. How 16? Because now we have 4 here inside and then we have these outside. So we measure what is the amplitude and what is the phase, and we then get 4 bits at the same, okay? With this we get only 1 bit at a time, in this we get 2 bits at a time, in this we get 4 bits at a time. Alright? But we have to be able to distinguish between a small amplitude and a big amplitude and a small phase and a different phase, 4 different phases. Actually, probably more than 4, because there is this angle, there is this angle, and there is this angle. 3 angles right there. So there are 12. So now you see how we combine the amplitude and phase, and we put a dot there which says now this means 1 1 1 1. Okay, 4 bit per each point. And so this is what is called a symbol. So here in 4 QAM you have 2 bits per symbol. There are 4 symbols. Here we have 16 QAM, we have 4 bits per symbol. And how many symbols are there? 16 symbols. Right? Now can you think of anything higher than that? Where will you go after 16?
64.
64. You can have 64 QAM. And then with this part, 64 times 4 is 256 QAM, and then 1024 QAM, and that's where the world is going. Previously, we could not do all these high-level QAMs because we didn't have that precise electronics. Even 4 QAM would require big vacuum tubes this large, and you need 10 vacuum tubes. Now with tiny transistors, we can do 1024 QAM and higher up, 2056 and whatnot. Okay, so we can send lots of bits per, okay, and when you send lots of bits per symbol, of course your error rate goes up, but if you have a good electronics, it will keep it controlled.